We're starting today with pulley problems. And so the other term, if you want to look this up later, you're probably going to want to write this down, that a lot of people will call these Atwood's machines. Okay. Atwood's. One word, not Atwood's machines. It's one word. I don't know why it looked like two. Why do they call it that? Probably because the guy, Atwood, we'll get to it. So the direction of acceleration is positive, just like we said. Any force that goes in the opposite direction of the acceleration is going to be negative. So if it forces and slows us down and works against us, that's a future concept. It will be slowing us down, and so we're going to make that negative. So is gravity negative at this point? The answer to that is it depends, right? You want to say no just because of the way I phrased it, but at the same time, we know that right here, if I've got this, which way in general does it favor? Does it favor the right side or the left side? Depends on if you want to go up or down, right? So in general, which one's going to go down? The right side. So I'm going to say that this puts pressure on the right side to go down, and that's because what's happening? What is this arrow? So we've got the force of gravity. But on the other side, about how long should I draw gravity? About half as much. Okay. So there is still gravity on this side. All right. And so now we clearly see, hey, look, I've got a gravity that's working for us and a gravity that is working against us. We know that it's going to favor the right-hand side. And so when I say what's our master equation? F equals ma. I'm also going to say that I can make a map of all my forces, and all my forces is what versus what in the big picture of everything. The force of gravity versus the force of gravity. So maybe I should put that this is object 2 and this is object 1. So which one's the positive one? Force of gravity 2 versus force of gravity 1, right? In other words, this is going to be positive. My net force is positive because my acceleration is going to be positive. And therefore, if it's going to move towards the right and favor the right-hand side, that this is going to be the positive one. We could put a positive in front of there, just sneak it in front if we wanted to. And that this is going to be the negative one. All right. And I keep on trying to say that it favors to the right because is it really going to move towards the right? It's going to move. This one's going to move down. This one's going to move up. And this one's going to move. The pulley is going to move clockwise, right? Clockwise? Is that the way a clock goes? Double check. I always double check. So this net force is the mass times acceleration. What mass am I going to have to move? Which mass is going to have this acceleration? That's a better question. Both of them. You're not wrong in saying 2, but also 1. So M1 and M2 end up with the acceleration. So net force equals ma. Well, that's the net mass moving at the net acceleration. Not just that, but you said FG2. What's FG2 equal to? Mass 2 times. And we're going to subtract off mass 1 times gravity. Did you want to factor? I don't care. If you factor this, you would have M2 minus M1 times gravity. And part A says to solve for the acceleration. So the acceleration, A equals, I'm going to move this to the bottom, M1 plus M2. All right. And in the midterm, I like to say it this way, that the difference in forces, right, because the masses are working against each other times gravity, So the difference in forces divided by, or the net force divided by the total mass gives me acceleration. Good. Okay? That's what we're saying. The net force divided by the total mass gives me my acceleration. And so it still works out just fine. But now we can plug in numbers. A equals 0.2 minus 0.1 over 0.3 times 9.8. And this is 1 over 3. So a third of 9.8. A third of 9.8 is 3. That's divided by 3. And then 2, 6. Meters per second squared. Are you good with finding the acceleration so far? If you were to look up how to find the acceleration of a pulley system, Google would give you this. But because you are in AP Physics, you must be able to justify it with this. If you plug it into this equation, it works. But you need to say why this equation exists. Yes, sir? Yeah, definitely. Alrighty, so we have the acceleration, but it also asks us for part B, the tension in the strings. Now, we didn't even draw the tension in the strings because we were worried about the big picture of the system. When I drew the big picture of the system, you had a downward arrow here and a downward arrow here because it's almost like you've got 100 grams tied to a string and 200 grams. And instead of gravity, it's kind of like that gravity is applying a force this way of 2 newtons versus a force this way of 1 newton. That's kind of the same concept. The only difference is that you draped it over a pulley, and now instead of it being a pulling force this way, it's gravity pulling it down, right? No difference. But what is tension? We didn't draw tension because tension happens to be this rope in the middle, right? If I were to worry about drawing tension, I would put it up here. And I should make it, if we're worried about the length, we made this one half as long. I should probably make it longer than this one, right? Because tension is what's going to move this one up. And is tension as long as this force, though? No. It holds it back, though. It keeps it from moving as fast. Okay, so I kind of targeted that this arrow would be longer than this line, but shorter than this line. And then they're about the same length. That's to say, if I can't use the whole system, can I use a subsystem to find the tension? Right? Because these are going to cancel out in the whole system, right? This upwards pull is balanced out by this upwards pull, and it's just kind of like doesn't make a difference on how fast it flies up or down, right? So I'm going to look at just a subsystem. What if I only look at one side of the problem? Do you want to start with the right side or the left side? The right-hand side? Sure. So the right-hand side has a mass of 200 grams, and it moves generally down, and there is an upwards tension that we need to find. T equals question mark. This one is F G equals mg. Now, if I'm worried about this, what's our master equations? F equals ma. Oh. F equals ma. But then I have my homemade equation based on my picture. My net force will equal what versus what? Right. Gravity. I already have that Fg equals mg. Minus tension. Wait, you told me F equals ma. And so I can just say ma equals mg minus t. And if I'm solving for t, t equals mg minus ma. And the mass is 200 grams, or 0.2. G is 9.8. Mass again is 0.2. And A is 3.267. My tension equals types in some numbers. I think it's 1.307. 1.3. What's the calculator tell you? Yeah? What you said, Mr. Kwan. 1.3. I really don't know. I missed it earlier today. Is it 1.3? You're serious?
1.28.
Okay. I'm going to put a box around it. I think it depends on where we round to. Is that it? Is that all we need? We could solve for it on the other side. Yes, you can. Wait, I didn't get that recorded. Mr. Kwan, wouldn't they be the same? Let's find out. Mr. Kwan, we take your word for it. We don't have to do this. No, let's go ahead. The net force equals MA. On the second side, we have the box of 100 grams being pulled up just as much as the other one, but being pulled down by half the gravity. Our net force equals, what's our equation this time? It generally moves up. So our equation is going to be built as tension minus mg this time, right? So I have tension here, and force gravity equals mg there. And so tension goes up and gravity. So it's flip-flopped based on our picture. We look at our picture and which way is it going? So we say MA equals T minus mg, or MA plus mg equals T. Instead of saying mg minus MA equals T, this is MA plus mg equals T. Our mass is 0.1. Our A is 9.8. No, what is our A? 3.267 plus 0.1 times 9.8. Wait, what do you mean it's the same? Did we prove it? Did we prove what we were trying to prove? Did we do what we're set out to prove? Okay, so it is the same. Good. Okay. Why? Because our equation was set out to say what is the acceleration, and for both of these boxes to accelerate the same way, you needed, and let's think through this, we needed the tension minus the force of gravity to give us the sum net force where the acceleration is the same. So there is a net force here. Is this a real force? No, this is the sum of all the forces. And the tension was so strong it overcame gravity to give us the net force. In the reverse, this is true, that gravity overcame tension to give us the net force. And so if gravity was strong enough to overcome tension, and I have gravity and I have the net force, I could say gravity minus this equals the tension. And if I know that tension is going to overcome gravity to give me the net force, if this minus this equals this, I could say these two added together should be the same length as this arrow, right? It's kind of like saying A minus B equals C. It's not kind of. It is exactly this. So then I bet you B plus C equals A. Same equation, yeah? And so we're doing the same thing here, but we're doing it graphically, saying that the tension overcomes gravity. So tension minus gravity equals this net force. So if I'm looking for how long this arrow is, and I know how long these two are, just add them together. Okay? The tension in the string. I don't typically do both on a test. Typically, you will want to conserve your time so you can check your answer. The easier way to check your answer is that this force of gravity is 0.98 and this force of gravity is 1.96 newtons. So when you solve for your answer of 1.3, what has to be true? It has to be larger than 0.98, but smaller than 1.96. So that's my general rule of thumb is look for the force, make sure that this force is between those two, and then you know you didn't flip-flop and go outside the scope of the problem, okay? It probably means you didn't flip-flop your signs wrong. Because if you flip-flop your signs wrong, you probably would have been like accelerating at greater than 9.8. And is it probable that this problem accelerates greater than 9.8 when your only available driving forces are gravity? It doesn't make sense to exceed 9.8. Yes, sir. Okay, so let's try it again. What do you mean try it again? It looks like it's the same setup. We've got two different masses. So I could automatically, and this is what the internet would say, that the acceleration equals m2 minus m1 times g over m2 plus m1. And I could use this equation. That's true. This is the Atwood's machine equation. But we need to be able to prove it. So we would need to be able to say that the net force equals ma. And then we need to say, what else do we need to say? We need to set up that the net force is a competition between our two forces of gravity. So Fg2 minus Fg1. That this is equal to the addition of the masses. It has to move both masses with some acceleration. And then this is m1g minus m2g, right? Minus m1g. And that's because the AP test, they'll be looking for your source equations. They'll be looking for some sort of intermediate step. And then here is our master equation that will help us get the last point, the right answer, okay? So if this was a 3-point problem, you need the source, you need to show your work, and you need to get to just about the right answer. Okay, so memorizing this is not enough. We need to have the beforehand as well. Right here we can start plugging things in. 3.2 minus 2 over 3.2 plus 2 times 9.8. Again, all of this numerator is the opposing forces, and the denominator is the total mass. So forces divided by masses gives you your acceleration. And did you get 2 point something?
Yes, 2.26.
Meters per second squared?
Yes.
All right. A is done. That was way faster than the way we worked it out for the first time around. Okay? We need to systematize it so that we're fast. Part B, the tension in the string. I mean, you don't have to be that fast. It's just I want you to save time so you can spend it elsewhere, right? So you can check your work. Part B, what's going on here? Do you want to look at the right side or the left side? The left? Honestly, I like 2 more than I like 3.2 as well. So we've got gravity going down, and in general, it will move up with tension, T. Fg of block 1 equals M1G. So we have our second law, F equals Ma. But what does our picture tell us? That the net force also equals what and what?
Tension minus gravity.
Tension minus mg. This is M1A equals tension minus M1G. I've got 2.26 plus 9.8 all times 2. That's close to 12 times 2.
24.12.
Okay, so 24. And that is more than 19.6 and less than 30-ish. So I've checked it already, kind of the quick way. Not a full check, but you know, this is also the 4th period I've done this, so I'm not going to do the other side. I trust that 24 is correct. Calculate how far the system will move in 1.2 seconds if the system starts from rest. This doesn't sound like a dynamics problem at all. This doesn't sound like forces. Kinematics. T equals 1.2 seconds. It says it starts at rest. VI equals 0. What other givens do we know? Oh, we solved for the acceleration. 2.26. Do not use 9.8. I'm scared people are going to use 9.8. It sounds like it's happened before. We're solving for x, the distance. X equals VIT plus 1/2 AT squared. That's 0. So X equals 1/2 2.26 T squared 1.2 squared. I'm not going to solve for it. You know how. I'm just going to introduce the next section, but we're done for today. I don't want to get too far ahead of the other classes. We have pulleys and surfaces. We've got a 3 kilogram mass on a level surface, a frictionless table attached to 2 kilogram mass by a light surface that passes over a frictionless pulley. Find the acceleration of the system. What's the only force outside of the system, or partially outside of the system? So part of it is inside the system, gravity on this side. The other part is the earth pulling up. And so gravity is the only thing that's not really offset by a balancing force. But here's the crazy thing. Even though gravity will be our only driving force, and so even though when we say net force equals MA, and that the net force on which object is this gravity going to affect? Which object is this gravity going to pull? Both. Oh, I thought you were saying both of them when you said 2 of them. I thought you were saying 2 of them.
No, I said 2 people.
Would you like to change your answer to both of them though? Yeah. I would like you to as well. So it's going to pull both of them. The force of gravity is going to pull both of them. And so when you say this net force equals MA, you're also saying that this force is powered by the force of gravity on the second box, right? And so you're going to say that both of them, M1 and M2, are going to be pulled by gravity of box 2. One force, 2 boxes. It's pretty much saying, hey, look, have you done problems like this before? One force with pulling 2 boxes. It's the same. It's the same. The only thing that I'm worried about is when we draw the free body diagrams. When you draw the free body diagrams, box 1, what is the forces on box 1? Friction's not available for us. It should be, but it's not.
Force normal.
Tension? Oh, maybe you said tension instead of friction. Yeah, force normal and gravity still exist. And I have seen so many people know that we're only going to concern ourselves with the tension, and they don't even play around with these. They don't even draw these 2 into the diagram. And if I ever ask you for a free body diagram, you need to draw all your real forces. These don't magically disappear. They are equal to each other, and therefore we're not concerned about them mathematically. But do they just disappear? They still exist, right? Okay. And so that's what I would be most worried about. So yeah, we know on the other box that we have gravity and tension. Most people forget about gravity on this other box. And then the normal force, the table holding it up. Okay. If you do have friction, it will hold us back. We'll talk more about it on Monday.